So here we have the first question of the FP2 test at Havant Sixth Form College on differential equations. It's an integrating factor question. It clearly is that because it's of the form, in order to use the integrating factor, it needs to be of the form dy by dx py q, where p and q are functions of x. And the idea of the integrating factor is that we can get it in exact form if we integrate, if we multiply this thing by the integrating factor. We can get it in exact form if we multiply it all by e to, what's the wrong way around? Multiply it all by e to the integral of p dx. But remember, it has to be in this kind of format for us to be able to use that. So we can't have anything here. So if we haven't to use the integrating factor. So, well, okay, so now we did that bit then is equal to cot x, 2 cot x. Do be careful to make sure you include any constants, any negative sign, because they're going to have a dramatic effect on the integrating factor, as you'll see. So the integrating factor equals to e to the integral of 2 cot x dx. Now that's in the C4 formulae. The integral of cot x is ln sin x. I think it's in C4 formulae, I'm pretty sure. But in fact, we should see it fairly clearly. If we write cot as cos over sine, cos x over sine x, we should see it fairly clearly as fitted into this format. So it really need not be in the formula book for us to know it. Indeed, it kind of irritates me a little bit that it is. So there we go. We can integrate cot very easily. So I equals to e to the 2 ln sin x. Okay, well that actually means that I need to get that into e to the ln sine squared x. So here we've now got the e and the ln kind of cancel each other out, so that collapses down to sine squared x. So we're going to multiply our formula here, our differential equation, by sine squared x. So we have, let's just write the cot x as cos x over sine x as well. So we've got sine squared x dy by dx plus 2 y sine squared x cos x over sine x, which is our cot x, is equals to cos x sine squared x. Okay, right, now playing with this, that gives us sine squared x dy by dx plus 2 y sine x cos x equals to cos x sine squared x. Now really it's kind of, well, I've done that just out of habit really, but it really, if the integrating factor is correct, and it is, it looks to be correct, in actual fact we can see that the exact form, without having to simplify here really, we should see, I just didn't want to, using this as a check to see it's exact really there, that it's sine squared x y. But in fact, if we've used the, and we can see that because if you differentiate 2 sine squared x, you get 2 sine x cos x times by y. Differentiate y, you get dy by dx times by the sine squared here. So we can see that it's right from the line above. So I think it is quite nice to have simplified to see that it is right. But in fact, if you've used the integrating factor correctly, we should find that we have the bit the integrating factor bit that's there, together with the y, will be what's in the exact form if we've done it correctly. So we don't really need to look that we should have seen without simplifying, or we could have assumed without simplifying that was it. But I've put this line in just to verify that it is in exact form, and we can integrate now. Okay, so that means it's equal to cos x sine squared x. Okay, right, now we can integrate both sides. So that gives me sine squared xy equals the integral of cos x sine squared x dx. Now, this if you can't see this, you need to practice your integration. I'm sorry to say, because it really is really of a standard written form. You can use a substitution of u equals sine x if you like faffing about with that type of thing. Go ahead. However, we ought to see that it's of this kind of form, f stroke x fx to the n dx. When we have that, it's of the actual thing is fx to the n 1 over n plus 1. It's kind of almost a reverse chain rule type thing, a kind of recognition case. So that means, changing back to blue pen here, that means sine squared y, the general solution, is sine squared xy equals to this integrated. Now, as I say, if we have fx equals sine x differentiates to cos x, so it's exactly of this form without any tweak whatsoever. So 1/3 sine cubed x plus c. So I have little sympathy for those who didn't see that in the test. That should have been, say, C4, you need to be practicing your integration. If we've done that, and I suppose we might decide, because it's easy enough to do, it hasn't asked for it in the term y equals to fx, so we may well be okay leaving it like that, but because it's easy to write in the form y equals fx, I'm going to do that. So divide through by sine squared, we get 1/3 sine x plus c cos x squared x is the form in the form y equals fx. I might reward the question for next year to actually make them do that final step. So that's it. Okay, and it should have been a nice gentle introduction into the paper. Often with the integrating factor, it's quite kind of pleasing in a way. It often collapses down to E ln. We're always trying to get this E ln thing together here so that it collapses down to something with neither an E or a ln, so they cancel. Not always the case, but probably more often than not we see the E and the ln collapsing into and kind of cancelling and giving an integrating factor which doesn't involve an E or a ln. However, not always, as we will see in the second question of this test, which I'll be posting shortly. Okay.